The next function to modify an atomic variable is called atomic compare and exchange. There are three values involved. Firstly, an atomic variable, an expected value, what we think this atomic variable has as value, and a new value that we want to write. Okay, let's look at the declaration first. And as you will see, there are 4 versions of it, but just look, we can take the simplest one, namely this one, atomic compare exchange strong. I will explain the others soon, of course. So we have a pointer to an atomic variable. We have a pointer to a variable with the expected value, and we have the value. And the value is what we want to write into the atomic variable, I mean what pointer points at. And if the current value of the atomic variable is the same as expected, I mean if it has the expected value, then we copy value into the atomic variable. And if it's not the same, then we instead copy the current value of the atomic variable into what expected points to. Okay, so let's look. Basically, these functions contain the following if statement. Namely, okay, and recall now, pointer is a pointer to the atomic variable, and expected is a pointer to a variable with the value that we expect it has or want it to have, and value is the value that we want to write to this atomic variable. Okay, so what we do is to check if the atomic variable has the expected value, and if that's the case, then we copy value into the atomic variable. So we use a star in front of the pointer to get what to get the value of what the pointer points at. So a star in front of each of these, and then we use a star again in front of a pointer when we want to modify what it points at. So a star pointer equals value means saving value where that points to. We don't modify pointer, we modify the memory location that pointer points at. Okay, so if this is if the value had the expected, if the atomic variable had the expected value, we give it a new value, and if not, we can know the current value of the atomic variable, since in the else statement we instead copy the current value of the atomic variable into this variable. Okay, now there are first let's look at this again, and again as we had for the atomic exchange, we had explicit, and then we could specify a memory order, and without explicit it was sequential consistency. Now what is added is strong and weak versions of this, and the reason for having that is that some machines have a single instruction which does exactly this, namely which can be used for this, okay, and other machines don't, but instead they implement this instruction, atomic operations, split into 2 instructions. That's the case for several RISC machines, because it's easier to get the high clock frequency by splitting this atomic instruction into 2 different instructions. Okay, and when we split it into two, it may be the case that we were not allowed to store the new value. I will soon explain why. Okay, so but what can happen with the strong? I mean, the strong always succeeds. It always behaves as it should on this, but the weak may fail. It's not random. It's not some error that has happened, but I will soon explain why. But it can fail, and if it fails, it does not copy, and it always returns false. As we can see here, they return false. Sorry, they don't necessarily return false, but they return a boolean. Okay. So, if it fails, I mean the weak one, then it returns false, guaranteed, regardless of if the value was as expected or not. Okay, so both of these, they return true if it could update the atomic variable. So how can we use this? Well, first we need to understand the reason for having the weak and having the weak compare and exchange function. And well, why? Well, the reason is that it may be easier to split the atomic operation into two instructions, and there are different names for these instructions. But well, here are three names for the load instruction. I mean, this is a special load instruction. It can be called load locked, load linked, or load and reserve. On power, it's load and reserve. And okay, and what does it do? Well, it performs the load, and also it so to speak makes a note in the machine that it is this CPU that loaded this value. Okay, and then it will do a store conditional. And the thing is here that this store, it may fail, and it fails if it is not okay, I should say it like this. If a different CPU has done a store between our load and our store, then it fails. Okay, why is this? Well, we want to have an atomic operation, and if it is we who load, add some amount, change something, and then store, without any other CPU storing in between our load and our store, then essentially we had an atomic operation. I mean, no one disturbed us, so it was atomic. But if we load, compute some new value and want to store back, but another thread has overwritten the value so that our loaded value is obsolete, then it's not atomic. It is, it's the opposite. So therefore it fails. Okay? Well, that's the case. So if we look at this, if processor P first does a load locked, and then it wants in the future do a store conditional, but a different CPU Q performs a store between the load locked by P and the future store conditional by P, then the store conditional by P will fail. So in that case, this weak return false, and we have to do it again in a loop. So let's look at a spin lock. A spin lock, well, it is a lock without the waiting queue, so there is no sleep for a thread that doesn't get the lock. It just keeps busy waiting until it gets it. Okay, so how does this work then? First we have this atomic int, and then an expected value, and then the value that we want to write to. Okay, so we want, okay, first we must say what means free and locked. If we say that value 0 is free and value 1 means that it's locked, then what we want to do is to lock this variable, I mean a. So that's the value that we want to write to it, and the value that we expect, I mean, I'm not sure if we expect it, but the value that we hope to see that a has is that it's unlocked. Okay, and if a is unlocked, then we write 1 to it, and we will get 1 from this, so the while loop, I mean the do while loop will terminate. Okay, so what we do here is the address of the atomic variable, the address of the expected value, and the value. It does not, we don't need the address of this int, since it's just the value that we want. But why do we want the address of expected? Well, it is because that this function should copy the old value of a into expected if the if statement was not true. I mean, if the condition was not true here. If a was not 0, then it will write the current value of a into this variable. Okay, and since this may fail spuriously, well, due to that another CPU did a write between the load locked and well, load locked or load linked or load on reserve, then we have to loop. Since if this sequence of load and reserve and store conditional failed, then we have to do this again. So this store conditional is an interesting instruction, because usually some instructions, well, not usually only, but all computers have some instruction to get the conditional value if something is true or wrong, using, for instance, a compare instruction. And this store behaves in the similar way, so that we can check if it succeeded or not, and then branch according to the result. Okay, so that's the reason why we need a loop for the weak version.